Good morning, good day, good night, whatever it happens to be. This is the torque notes and practice problems, and I'm going to go ahead and run down through this so fifth and sixth period can get caught up from the snow day. And on the very first one, it told you to define torque. And Jessica, Vanessa, if you don't mind, give me the definition of torque. Very good. It's the work done in a circle, otherwise known as the product of the force times the perpendicular lever arm. Now, I want anybody that's watching the podcast right now to feel free to stop this at any time, because I'm just going to fly right along here so we don't take up so much memory, and to go ahead and write down the definitions. Number two, I want you to write down the full formula for torque. And Caleb, go ahead and give me that. Great job, Caleb. Exactly right. It's the sort of backwards J, or it's a T with a little tail on the end. We've already used T for little t for time. We use big T for the period, or seconds per revolution. So we're going to use this little backwards J, or a little funky looking T. It also in your book will look like this great big broad T right here. It's actually the Greek letter tau, as in dry off with a tau. And it's the Greek letter, since all these stuff that goes around in a circle has to do with Greek. This is work done in a circle, or torque. Now, the next thing it says is to give the full formula for it, so it's F times L. Well, if you remember when we did work, the work formula was F, or force times distance. Well, the lever arm is going to be the distance from the axis to the point of force, but it has to be the perpendicular, and that's what this little upside down T means, is perpendicular force. Another way to write it, and the most best way to write it, is force times lever arm times the sine of theta, and we'll get to that in just a second. And that was actually 1B. Number two is the definition of a lever arm, and that's the distance from the axis of rotation to the perpendicular force. And we did this little lab in class where you had to hold a ruler stick. And so here's my little hand holding the ruler stick here, right there. And here's the ruler stick. And so therefore this right here ends up being my pivot point. And then we hung a weight over here. Well, it's the distance from this pivot point to the actual perpendicular weight. You see how that makes a right angle? So that ends up being your lever arm for that particular little lab. And then lastly but not leastly, what we did was it's not lastly but not leastly, we did in 3 and 4. We did this little problem here, in which you had to figure out the torque on a door that had 100 newtons of force on it, that was placed at 90 degrees, and it was 1 meter away from the axis. So I used the formula up here for torque of FL sine theta. I put in the F of 100, the lever arm of 1, and since it was a 90-degree angle, I put the sine of 90, and that comes out to 100 newton meters. If you remember, work was also measured in newton meters or joules, torque, usually you just hear about it measured in newton meters. In the English system, when you buy a transmission or you talk about engines, you might hear about foot pounds. Well, you got to remember, if the torque is force times distance, in the English system, force is measured in pounds, and distance is measured in feet. So therefore, a foot pound is a measure of torque in the English system. And then we're going to number 4. You had the same door, but this time instead of pulling at a 90-degree angle, we pulled at a 45-degree angle. And so I put in the sine of 45 this time, and if you notice, the torque went down to 70.7. So the more right angle that you pull the door open with, the more torque you're going to end up having. All right. And then number 5, we have a 220-pound man sitting on a seesaw. Now, you might have remember doing this one before, back when we did the work on the left equals work on the right, or the lever lab. So I have myself sitting on the seesaw there. I'm the guy that looks like the Muffin Man. Have you seen the Muffin Man? The Muffin Man? The Muffin Man, the one on Drury Lanes. Anyway, I placed the 220-pound man 1.5 meters away from the fulcrum, and you have to figure out where to put my beautiful wife over here in the green dress, who weighs 125 pounds. Now, she's very fit. And so I'm figuring out where to put how much length or distance to put her away. So I got the torque on the left has to equal the torque on the right. So FL equals FL. I put in the 220 for me. I'm 1.5 meters away. I put in 125 meters for my wife, and divide both sides by 125, and that gives you a length of 2.64 meters. And now you are officially caught up in 5 minutes of everything we did in 50 minutes on Tuesday. Have a great day, and we're going to continue on now with number 6. Bye. This is number 6 on the torque practice problems. And what you have here is a chandelier. Now, this might sound a little bit strange, but sometimes you can't hang chandeliers. That's like, I can't talk today. This is like a chandelier is a light. Okay, it's one of those big fancy lights that you see in dining room balls and stuff like that. But sometimes, like in our Capitol, they can't hang them straight down because the dome is right overhead. So in this case, we have a chandelier here that is going to be supported by a set of cables. And one is going straight across like this. Okay. And I'm just going to make an imaginary line. That was good, Jeff. Oh, for goodness sake, what the heck? Go away. I don't know. That's the dome, that's right. I don't know where that came from. It's drawing another one. Hold on, I'm going to stop. I'm sorry you didn't hear that great big round of applause that this class just gave me here. Let me erase this. All right, good. Now, the chandelier is being held up by a couple different strings, I guess, or cords. One that goes straight across, and then one goes up like this. And the one that goes diagonal is at a 60-degree angle with the vertical. So that purple line is an imaginary line. And how much did they say the chandelier weighs, Giselle? Very good, 1,960 newtons. Okay. So if it weighs that much, that means that one of these cords has to be holding up with that much as well. And so exactly right. The lab that we did before was that pull-the-pin lab where you had to keep all the strings the same. And there were 4 different steps that we did in each one of those. And does anybody remember what the 4 steps were? Very good. You found out the X direction. Great job. And the next one we did the Y direction. And then you did the Pythagorean theorem. And then you did the tangent. Well, on this one, it's a little bit easier. You don't have to do all those steps. But let's just start off with one side of it here. I want to find, first of all, what is the force on each one of these strings? That's what the question's asking me. So I'm going to say this is the force of A. And over here is going to be the force of B. Here we go with the circles again. Okay, so let's find out how much letter A has to be pulling in the X direction. Well, isn't the chandelier sitting still? Well, if it's sitting still, what do all the forces have to add up to? 0. So I'm going to say that the sum of all the forces here, which my pen's not drawing now, this is really nice. Okay, the sum of all the forces has to add up to 0. And what are all the forces pulling in the X direction? Well, there's chord A, and there's also part of chord B. Everybody with me there? So let's find out what chord A is by figuring out what chord B is. Now what I'm going to do here is I want you to look at this blue force right here on this black line. And notice that how much is that blue force having to pull up with? Let's go to, who do I want to pick on? Hannah. How much does it have to pull up with? Very good, 1,960 newtons. Because B is the only one pulling up. Which way is A pulling? To the left, right? So B has to support all that weight. Well, therefore, B is actually pulling 2 different directions. It's pulling up, but it's also pulling over like this. Here we go with the circles again. That's good, Jeff. All right. Oh, my gosh. 1, 2, 3. Oh, sure. I'm sorry. Here. Look, oh heck, we're still recording. Whoever knew. God bless. This is ridiculous. All right, now we got a snowman. Okay. So therefore, now that you have a right triangle up here with force B, and you know one of the sides, we are trying to find side, either the opposite side here. See how the blue side is going to be the opposite side? Okay. What side is the pink side? The adjacent. Well, let's think about what you know. if you are trying to find the opposite side, see y'all, have a great day, guys, and you're given the adjacent side, what trig function to use? Let's go to Sarah. Very good, tangent. Because tangent is OA, or TOA. Everybody with me? So I'm going to cover up the O, and when you cover up the O, what's the formula, Sarah? Tangent times adjacent. So if I want to find out how much B is pulling in the x direction, I'm going to take the tangent of theta, which is 60 degrees, times the adjacent side. And what's the adjacent side? 1960. Very good. All right. Now, this side is pulling to the left. Which way is FA pulling? Which way is FA pulling? To the left. Very good. So it has to be negative, right? So a negative FA plus a positive FB is going to equal to 0. So now what I got to do, I got to figure out what all this equals. So I'm going to say FA then, I don't know why I'm writing it in blue, it should be in red. FA is therefore going to end up equaling 394 newtons, but since it's pulling left, you have to make that negative 394 newtons. Okay, 3,394. Thank you, Caleb. Now the easy part is this: you got to figure out what FB is. Well, what side of the triangle, Julia, is FB? That black side, since it's the longest. What side, is it opposite, adjacent, or hypotenuse, is this black side here, FB? The hypotenuse. So on this one right here, I'm looking to find the hypotenuse. And what side, once again, Chance, am I given right here, the green? Or the pink side, rather, which is written in green? What side would that be? Very good. It's the adjacent side. Okay. And Chance, whenever you have adjacent over hypotenuse, what trig function is that? Exactly right. It's cosine. So what I'm going to do here is to figure out the hypotenuse. I'm going to cover up the h. When you cover up the h, I'll simply take adjacent divided by the cosine. So that means that FB, let me write it in blue here. Gosh, these freaking circles. It's now here. All right, so therefore FB is going to be equal to, since it's the hypotenuse, I'm going to cover up hypotenuse. It's going to be equal to adjacent divided by the cosine of 60 degrees. Once again, what's the adjacent side? Let's go to Jordan. What number are you going to put in for the adjacent side? 1960. Very good, Jordan. And divided by the cosine of 60 here. And when you take the 1960 divided by the cosine of 60, you end up getting 3,920 newtons. And that's going to be that diagonal force there. Zach just asked a great question. He said, how come the force of the one doesn't add up to the force of the other? Which way is FB pulling? So not only does it have to pull across, but it also has to pull up. So you have to add those two forces together. And that's why FB is much, much more than FA, because FA only has to pull across. Only in the x direction. So if I were to take FA's x direction and FB's x direction, they would add up to 0. Okay, good question. The question here was, is this equation with the cosine, is that y? No, actually I'm solving for the hypotenuse. I'm actually solving for that black line here. So I didn't have to do all these steps because a lot of it was given to us. There was more information given to us, so I didn't have to go through x and y and then Pythagorean theorem and all that. I could just use what was given. And since I was given the adjacent side and I was given the angle, all you have to do is cover up the hypotenuse and solve for that. So if I cover up the h, it's adjacent side, which I know because of the weight, and the cosine of the angle, and that automatically gives it to you. The next great question was, could I just skip the first step and not solve for this FA? Well, the question actually asked you to find both FA and FB, so that's why I had to do that first step. Great questions, guys. I'm sorry I keep pausing it. Okay, number 7 gets a little bit more challenging here. And what you have on there, you got a uniform beam. Uniform means what? All the same. So it's straight across here. And this beam is going to have a mass of 1,500 kilograms. And how long is it? 20 meters, right? So the middle of it's going to be right here. So the whole thing is 20 meters long. And that 1,500 kilograms would be acting right smack down in the middle like this, wouldn't it? So that red line is actually going to be the weight of the beam. Now, over here, I have a printing press that's even bigger. So I don't know why I made it so small, but this thing is 15,000 kilograms. And it is 5 meters away from the edge. And then what is the force? You have to figure out the force on each support beam. So I'm going to have force, let me just call this 1 and 2. I think it'd be a better way to do it instead of A and B. So I have this as force number 1. This is going to be force number 2 over here. Now, remember the other day when we were doing the ruler stick lab, and as the weight got greater and greater, your hand wanted to rotate? So if I were to kick the leg out on F2, what would the table do? It would fall. But it would fall in a circle, wouldn't it? Because it would want to fall down from force number 1. Okay, if the table is standing still, what do all the torques have to add up to? 0, okay, because there's not going to be any torque on it. So what I'm going to do now is I'm going to say this. The sum of, I'm going to say the sum of all the torques have to equal 0. Well, there's one torque that's caused by leg number 1. And there's one torque that's caused actually by the weight of that beam. Because even if the printing press wasn't on there, if you removed one of the legs, that weight of the beam would actually cause it to fall. Okay, so this is the force of the beam. I'm going to put a little B there for the beam. Coming down here, I should have drew this in blue. That's going to be the force due to the printing. Here we go with the circles again. Jeez. So that was the force of the printing press. Over here, come on. It's going to be the torque of the printing press. I'm going to use as a P, not a circle. All right, and then lastly but not leastly, I'm going to have this is supposedly the force of the printing press. There we go. And then finally, I have the torque of number 2 over here. The issue is I don't know those torques, so you have to fill in or substitute a formula. So Jessica, what's the formula for torque? Very good, force times lever arm. So I'm going to have the force times lever arm of number 1 plus the force times the lever arm of the beam plus the force times the lever arm of the printing press. So all these are torques. I'm just writing the same thing over again. I'm just filling out the formula. And then we're going to plug in numbers. And then I'm going to have the force times the lever arm of number 2. Okay? Well, isn't force the same thing as weight? Okay? So therefore, I'm trying to figure out what is the force on number 1 and the force on number 2. Well, there's a problem. You have 2 unknowns, so I got to get rid of one of them. All right? So watch what I do. If I knocked out leg number 2, wouldn't everything rotate around number 1? In other words, the table would fall in that direction, correct? So what I'm going to do is I'm going to pretend like number 1 is my axis. Okay? Everybody with me? So let's say I knocked out number 2, and everything's going to rotate. What would be the lever arm if leg number 1 was right on top of the axis? Was right at the axis. Careful. It wouldn't be 20 meters. It would be just 0 because it's right on the axis. Okay? So watch what happens here. What's anything times 0? 0. So that gets rid of one of my unknowns by doing that. Okay? What's the force of B? What's the force of the beam? 1,500 newtons. But you got to remember it's mass times gravity. So I got to take 1,500 times what? 9.8. Very good. Now, where does the weight of the beam act? Right smack in the middle. And how far away is the middle from the axis? 10. Very good. So it's a 20-meter beam, so it's 10 meters away from the axis. So now we just fill in the printing press. The printing press is 15,000 times what number? 9.8. Very good. At least I don't have any circles right now. How far is the printing press from the axis? 15. Because it's 5 meters away from this edge, so it must be 15 meters away from the axis. And then we have force number 2, which we don't know. What's the lever arm of force number 2 from the axis? 20. Okay? So now all we do is solve for force number 2. So we're going to bring all these things in. So I got 0 equals 0 plus. See what? We're going to fill out all these numbers and come back to the podcast. Okay, so what I did here is when I multiply these out, I got a negative 147,000. That negative becomes negative because that net 9.8 is negative. It's acting down. Okay. The printing press is also pushing down, so that's a negative 2,205,000. When you put these together and then shift them to the other side of the equal sign, I now get a positive 2,352,000. What do you have to do to both sides to get F2? Page, divide by 20, very good. And why is this not working? There you go. And so when you now divide that by 20, the 20s cancel out, and you're left with an F2 equal to 117,600. Good job. Now, which way do you see that? Positive or negative? Positive. Which way does the leg of the chair have to push? Up, and that's why it's positive. So all the forces have to add up to 0 now. So I got the force of leg 1, which I'm now going to figure out what it is, plus the force of the beam, plus the force on the printing press. Friggin' circle. Feel like squirrel. Squirrel. Why did my writing disappear? All right. Am I still recording? Oh, good. I put that on that's so nice that I put that on the podcast. All right. So now I have the force of the printing press plus the force of number 2. So now what we're going to do is we're going to fill in all these numbers. Which one don't you know? F1. I don't know F1. That's what I'm solving. The force of the beam, once again, is 1,500 times 9.8. And that ends up giving you somewhere in the general vicinity of, how about a negative 14,700? So, what? Hold on. Yeah, that was a great question, guys. They want to know how come it's not 147,000, it's 14,700. You're not multiplying it by the lever arm down here. It's just force, not force times lever arm. Okay? So now you do the same thing with the printing press. So it's 15,000 times 9.8. And that ends up giving you somewhere in the general vicinity of 147,000. And that's also negative because it's going down. And I don't know why I just put F2 there. Hold on. Then you have to place in F2, which we got up here. And that's a positive 117,600. And then when you add all these things together and take it to the other side, you get, so it ends up being a negative 44,100, but when you flip it to the other side, it becomes positive 44,100 newtons. Right. Everybody good? Thank you, Hannah Worth, for catching me. This should say F1, which is not right. And that should say F1. Special thanks to Hannah Worth. All right. Not only special thanks, but a shout out to Hannah Worth. Thanks. Okay, I just realized on number 8, I have a real big boo-boo here. Actually, it's a real small boo-boo because it says a 70-Newton woman. Guys, a 70-Newton woman would weigh, I figure a Newton is about an apple. So you're talking about a woman that weighs about 70 apples. So, yeah, it's not that, she's not that big, maybe about 30 pounds. So this is a very petite midget. All right, so no offense against all you vertically challenged people. All right, so I got a woman here that's pushing down with 70 newtons of force. You're going to love this podcast. All right, can't wait for the parent response on this one. All right, she stands at the right end of a diving board that has 60 kilograms of mass in it. So remember, that's mass, that's not weight, where this 70 newtons is weight. And the diving board is 4 meters long, so where's the weight act of the diving board? At the what part? Yeah, it acts at the 2 meter, because it's a uniform diving board. So its weight, the weight of that diving board is acting at 2 meters, not the 4 meters. Right? It says if a bolt holds the left-hand side down, so over here there's a bolt that's holding this down. I guess I should move this over here so you can see that's right there in the end. All right. That works. It says this, at the left end, a fulcrum holds it up and it's 1.5 meters away. So that'd be about the 1.5 mark right here. So from here to here, which it's not drawing, this is 1.5 meters. Find the force on both the bolts and the fulcrum. So I have to figure out what FB is. That's the force on the bolts. And this would be the force on the, here we go with the circles again, on the circle. So what was the formula that we started off with the last problem? It was the sum of all the torques, and then the forces was second. Good job. At least somebody was calling out there. So I'm going to have the sum of all the torques is not writing. The sum of all the torques. Good job, whoever said that. So I'm going to have the torque on the bolt plus the torque on the circle. Here's the force on another circle plus the torque on the, we'll just stop. So this is going to be the force on the beam, which is still not writing here. Just hang in there with me. There we go, force on the beam. This is going to be the force on the fulcrum. It's not force, it's torque. Torque on the fulcrum. That's actually a T, or a tau. Plus the torque due to the actual weight of the diving board. I'm going to put a D here for diving board. Plus the torque of the girl. So I'll put a little G over here for the torque of the girl. But you got to remember, you don't know all the torques, so we're going to fill in FLs for each one of those. So I got F times L of the bolts plus F times L of the fulcrum plus F times L of the diving board. Here goes another circle.
Calculus and physics.
And then we go straight to the force times the lever arm of the girl. Well, now you got to fill in all these things. Okay? So I'm going to have two things that I don't know that are unknowns. One is the force times the lever arm of the bolt, and one is the force times the lever arm of the fulcrum. So therefore, I'm going to make one of these 0, or make one of these the pivot point. I think the best pivot point to make would be the bolt. So therefore, if the bolt is the pivot point, and you push the fulcrum out of the way, the diving board would fall this direction. Okay? It would torque. So if the bolt's going to be my pivot point or my axis, it would have a lever arm of 0, and therefore I could get rid of one of my unknowns. Then I'm going to put in the force of the fulcrum, which I don't know. That's what I'm going to try to find. Now the fulcrum is 1.5 meters away from the bolt, so I'm going to put in a 1.5 for my lever arm there. Then I'm going to put in the force of the diving board. Well, the diving board is 60 kilograms, but kilograms is a measure of mass, so I got to multiply that by 9.8 to get the weight. And then after you multiply by 9.8, the diving board's center of mass is not at 4 meters because it's 4 meters long. It's actually 2 meters because the center of mass would be right smack in the middle. And then I'm going to put in the force of the girl. Well, the force of the girl is 70 newtons times her length, and she is all the way across to the other side, which would be 4 meters. So now I got to add up all these numbers here and figure out what we got. All right, so when you put all this stuff together, don't forget that the girl is actually pushing down, so that should be a negative 70 newtons. Hello, a negative 70 newtons, very good. And this is also going to be negative here, this negative 9.8, because the beam's weight is pushing down. So when you get all this, it ends up being this F here. Let me go ahead and write everything out here. Come on, please work. There we go. I got 0 equals F times 1.5. That's 1.5, not 0.15 for all you dyslexics. Plus 1456, and that's negative 1456 because all this is acting down. When I take that 1456 to the other side and divide it by 1.5 to get F, the force of the fulcrum that the fulcrum's actually holding up ends up equaling 970.6 0.6 newtons. Now that's positive because which way does a fulcrum go? It pushes up. Now that you got that, you have to do the easy part. So after I did the sum of all the torques, we now do the sum of all the forces. And so I'm going to put the sum of all the forces here. Since it's sitting still, it's have to equal? Exactly right, 0.
0.
Thanks, Jack.
You're welcome.
So we're going to put the force, oh, here we go with the circles again. So yes, anytime something blocks me, just let me know. And Tony, I just want to let you know that you're one of the biggest assets in this class. All right, and if you would, I got the force of the bolt now, plus the force of the fulcrum, which we just figured out what that was. Oh, here we go with the circles. Come on. Ugh. All right, so I had the force of the bolt plus the force of the fulcrum. And then I had the force of the diving board plus the force of the girl. So, and all those have to add up to 0. So I'm going to plug all these in now. Well, the force of the bolt is what I'm trying to find. It's going to be positive because it's pushing up. The force of the fulcrum I just found of 970.6. The force of the diving board, well, the diving board, if you remember, it weighed 60 kilograms, but that's not the force, that's the mass. So I'm going to take the 60 kilograms times negative 9.8 because it's going down. And then the girl was that microscopic little midget of negative 70. And we'll talk about it once again. That was a mistake. Probably should have been 700 newtons. But we then have to figure out what the force of B is. So I'm going to put all this together. I don't know if anybody just heard that duck that was, I think it's Duck Dynasty here in the class. So I don't need somebody's chair. So we put all it together. It was either that or a white elephant. All right, now. So, somebody had the extra sausage. So therefore, the force on the beam ends up being 312.6 newtons. All right.